Hi everyone. We're going to calculate the pH of this sodium carbonate solution, or A-2, and the color of the indicator again suggests that the pH is basic, but let me test it with pH paper and show you what I get. Ooh, that's basic. That's almost off the charts basic. I don't know if you can see that, but that is about a pH of, I would call it over 12. So when we calculate the pH of this solution, if we don't get a basic pH, we've done something wrong. And remember, since carbonate was used to prepare this solution, A-2 better have the highest concentration, and the concentrations of HA- and H2A better be small. Here we go. So here's an example of the unprotonated form. We've got a solution of 0.05 formal sodium carbonate. You've got to recognize that carbonate is A-2, and we're asked to find the pH and the concentrations of all these different forms. Well, since we prepared the solution from carbonate, or the unprotonated form, it should have the highest concentration, and these two forms should have the lowest concentration. And because we use the unprotonated form, that pH should be basic. So we've got some Kas and pKas. Let me, so I just don't make any stupid mistakes, remind myself that this is the equilibrium for Ka1, and that this is the equilibrium for Ka2. I just don't want to make any stupid mistakes. And if we've dissolved A-2 in water, what happens? Well, it's going to behave, as you're probably thinking, as a weak base to form HA- and OH. So we probably should calculate a Kb value here, and that'll be Kw over, and then the question is, which Ka do we use? Do we use this Ka1 or do we use this Ka2? Well, it's very good that I've written these down because I think this will help us. Look at our Kb. It contains A-2 and HA-. Now, which one of these Kas contain A-2 and HA-? It's Ka2. So we would use Ka2 to calculate the value of Kb, and I got 2.1 with an insignificant 3 times 10 to the -4th. And I only have 2 sig figs here, even though Ka2 had 3, because I only use Kw with 2 sig figs. Now, we've got to think about what what HA- does in solution. Yes, it can accept a proton from water in a Kb reaction, but should we worry about it? And the answer is no. We can ignore the Kb reaction of HA- because this Kb is going to be small. And that allows us to treat A-2 as though it were monobasic, I should say. Treat A-2 as though it were monobasic. So we all know how to find the pH of a weak base, and we're going to use quick and dirty, but just in case quick and dirty fails, I will write down what we have at equilibrium. That'll be 0.500 formal minus X for A-2, X for HA-, and X for OH. But let's try quick and dirty. Fingers crossed. Let's hope it works. OH is equal to the square root of our Kb, which is 2.13 times 10 to the -4th, times our formal concentration, that's 0.050 formal. And I got for OH 0.0032 with an insignificant 6.5 molar OH, and that's not less than 1% of this formal concentration. It's not less than 5% of this formal concentration. This OH concentration is about 6.5% of this formal concentration of A-2. So quick and dirty failed. We're going to have to use the quadratic, and maybe I'll just set it up for you. We would begin by saying Kb is equal to products over reactants, so that would be x squared over 0.0500 formal minus x. And I think I'll let you use the quadratic on your own. You should get that x is equal to 3.1 with an insignificant 6 times 10 to the negative third molar. And x, remember, is our OH concentration. So we can get the pH, and I got a pH of 11.50, which is basic, which is what we would expect when we prepare a solution from the unprotonated form. So we've gotten the pH. Can we get any of these other concentrations? Sure we can. We solved for X, but not only is X OH, it's HA minus. So HA minus would just be that OH concentration that we got, which was 3.16 times 10 to the negative third molar. We got that. And I think we can get the A-2 concentration. A-2 would be this formal concentration minus X, so that would be 0.0500 formal minus 3.16 times 10 to the negative third molar, and I got 0.0468 molar for A-2. And notice how close that concentration is to the formal concentration. This is making sense. The only one left is the fully protonated form, which should have a low concentration. So to get H2A, the fully protonated form, there's more than one way to do it. Looking at everything that I have here, I'm tempted to just use Ka1. Ka1 would be H plus, and if we know the pH, we can get H plus times HA minus, which we know, that's this, divided by H2A, and maybe I'll let you work through it. H2A you should get is equal to 2.2 with an insignificant 4 times 10 to the negative eighth molar, which is small. Now, sometimes students think of a different way to get H2A, and it's pretty clever. They say, well, why don't I just use this Kb reaction for HA minus, because it produces H2A, which is what I want, and OH. And I would say that Kb is equal to H2A, which is what I want, times OH, which I already know, over HA minus, which not only do I already know it, but HA minus and OH are equal, you remember, and they cancel. So H2A would just be the Kb for this reaction, which you can easily get by taking Kw over Ka1, and it would be what we got here, 2.2 with an insignificant 4 times 10 to the negative eighth molar. So you can get H2A however you want, whether you use Ka1 or you use Kb2, I would call it. Either way is fine. But for a solution prepared from A-2, we got a basic pH. A-2 had the highest concentration, and HA- and H2A had the lowest concentrations. Let's take a look at this on the fractional composition diagram. Here it is. Again, that's a plot of alpha against pH. And we got a basic pH for our solution, didn't we? We got a pH of about 11.5, and at that pH, A-2 has the highest concentration, HA- has a very low concentration, and H2A, shown in red here, has the lowest concentration. So I hope you try these calculations on your own. I hope you don't have to use the quadratic, but maybe you will. Hope you enjoyed the video, and thanks for listening.